Greetings everyone, you're watching NeriChem. This is question 7 from the HSC 2018 paper. Let's get into it. Which diagram represents ionization of a weak acid? Okay, what is a weak acid? An acid which is weak does not like to dissociate. So if we represent an acid as HA, where A stands for acid and A is just a proton, we know that HA will be most abundantly undissociated. So let's look at the different forms and shapes which we have in the question. We have the key at the bottom, tells us that this is a weak acid. So A would be the black circle and the proton would be the small black circle. This is water, so evidently the big white circle is oxygen and the bottom is the hydrogen. So if we look at A, we have, I'll call this 1. This is clearly a hydronium ion. Now, a hydronium ion forms when we protonate water. And a hydronium ion is H3O+, but this is an equilibrium, so it can either be to the right or to the left. The second shape we have in the question is the acid in its anionic form, so this means it has lost its proton. If we look at B, we see 3, which is just the weak acid we see below, and 4, which is a neutral water molecule. Now, we said at the beginning weak acids don't like to dissociate, so we need to find one of these 4 panels where we see very few, although there can still be some, but very few weak acids dissociated and mostly undissociated. So we know that A cannot be the correct answer because you can see clearly that all of the weak acid molecules are dissociated. So that A would probably correspond with something like HI, hydroiodic acid. So if this was an iodide molecule, A could be HI. The problem is HI is a good acid. It's not a weak acid. So can't be A. Could it be B? Well, what we see in B is 1, 2, 3, 4, 5 neutral water molecules and 1 molecule of a weak acid. And none, well, the only weak acid molecule that we have is undissociated. So it's probably not a weak acid just because it's 100% undissociated. And although a weak acid might be close to 100%, it's not exactly 100%. So not B. Also, fun fact, if you look at the difference between B and B and D, they're pretty much the same, except we're just changing the numbers of molecules. So for the same reasons, D is not the correct answer. It just has a different amount. That doesn't change anything. So then, of course, we have the final culprit, which is C, which is going to be the correct answer. Why is it the correct answer? Well, we see that 2/3 of the weak acid molecules are undissociated, so the majority, and 1 is dissociated, so we know C is the correct answer. Fun fact, and this is just making things intense because I enjoy it. The problem with the shapes in the diagrams, which is, I know, a silly thing to point out, but I enjoy it. So the sphere makes it seem as if it is a single atom, and the only acids which have 2 atoms involved are the group. So you have the halogen, which is group 7 on the periodic table, with a single proton. So you have hydrogen fluoride, hydrogen chloride, or hydrochloric acid. Then we have hydrogen bromide and hydrogen iodide. Fun fact, in case you were wondering, the strength of the acidity increases down the halogen group, which is funny because you think hydrofluoric acid, that's so scary, that's really corrosive. Wait, corrosivity is not the same as acidity. These are 2 different things. In fact, so you take HF and you dissociate it, you get H plus and F minus. Acidity simply describes how much, the degree of dissociation, but the corrosivity of hydrogen fluoride comes from the reactivity of the fluoride anion, which has nothing to do with the acidity. Hydrogen fluoride is the weakest acid of all of this list. So that's just a fun fact. And the reason it comes to mind is because the black balls make it seem like it's a spherical anion. And of course, a weak acid might be citric acid. So I will draw citric acid just for the fun. You have the carbonyl, and then you have a carbon, and then you have the center, and then you have another group, and then this goes down, another carbonyl, another OH group, and I think this is an OH. So this is a weak acid. Hydrofluoric acid is also a weak acid, but the actual difference in the radius between a fluoride anion and a hydrogen proton is relatively small. And if you look on the diagram, the black ball with the checkered pattern is a lot bigger than the hydrogen proton. So it's probably not dimensionally or geometrically equivalent to HF. But the problem is with citric acid is that it's not a spherical ball, or at least it doesn't look as spherical as hydrogen fluoride. So bit ridiculous, but if I was to contact the composer of this question, I would have made the black checkered ball a lot smaller so that it could be easily identifiable as HF, which would make the question a lot more fun in the eyes of those who can see these things. So I hope that was useful for all of you, and see you in the next question. Goodbye.